Hey everybody, video 2 for solutions. Let's get right into the vocabulary. Take that big bad quiz when we get back from break. So define the specialized vocabulary of the solutions unit. A solution. There's some colored ones. Specifically, a homogeneous mixture of solute and solvent. Man, there's 4 words in there that are just kind of loaded to give this very specific definition of solution. When I talk about detail orientated, that's what I mean. The word solution has this connotation, this hidden meaning of all of these things that have to be in there. Homogeneous, same throughout. Mixture, 2 things. What are the 2 things? The thing that's being dissolved, solute, and the thing that is being doing the dissolving, the solvent. So it's kind of a loaded thing there, right? There's a lot of implied knowledge just by that one word solution. So all those other things have to be there. Let's get into solute and solvent. Make sure you know what those things mean to make a better understanding of solution. So solute here is the powder, the part of the solution that is being dissolved. A lot of times you'll see it's in the smaller quantity usually. For the most part, for us, it's a solid. Sometimes it's a gas. I don't think it's ever considered a liquid, because if 2 liquids are dissolving or mixing, we call that miscible, not solute, solvent. Okay. Solvent in this case then is the water, which is doing the dissolving. So this is the part of the solution that does the dissolving. It's usually a liquid. A lot of times it'll be water, not all the time. So we'll change up. Table G is all about water. Speaking of water being the solvent, and here's a picture of sugar dissolving in water. This is an aqueous solution is a solution where specifically water is the solvent. So it has a code name. It's called aqueous, has that little symbol AQ. I think that most of us are familiar with this, and hopefully after this, everybody is completely familiar with this. Alloy. Here's a picture where some of us might be familiar and some of us might not be. Common use of the word alloy is alloy rims. What this applies is a solution of 2 or more metals. Literally, I'm going to liquefy 2 metals and mix them together. So a common one would be brass. Brass is not on the periodic table as an element. Brass, I believe, is a mixture of copper and tin. And if I melt them and I mix them and I let them resolidify, I have a new metal called brass. So it's a solution of 2 or more metals as an alloy. Solubility. Notice they're soluble on the same page. Notice there's dissolve and dissociate. So please take a moment. We have to be able to distinguish these words and their definitions, and they're slightly off. So like solubility and soluble, one's I think one's a verb and one is like an adjective or something like that. So like you're better at English than I am, but pay attention to the nuances because it's important. Sorry, big bad table G. Here it is. We will learn how to read this thing, and this tells us about solubility. Notice it's on the chart, solubility curves. This is the measurable amount of a solute to dissolve. So how much? Solubility is how much will dissolve. That's how I think of it. So it's the measurable ability to dissolve. How much will dissolve? Okay. Then that leads us to dissolve. Dissolve, we have experience with dissolve because sugar dissolves in water, and I stir it up and there it goes. Okay, so it dissolves. So when a molecule of a solute breaks apart from each other, the molecules break apart, taking the phase of the solvent. That's key. So solid sugar is molecules of sugar physically bonded next to other molecules of sugar, and when they dissolve, they break apart from each other. And that's it. And then all of a sudden, that solid sugar is now in the liquid phase. It's not liquid sugar, it's dissolved into the solvent, and each molecule is surrounded by water. Each molecule of sugar. Okay. Dissociate is a different thing. Dissociate, and here's a good picture where the CLs and the OHs or the NAs break apart, and in the water, you see how they're surrounded by waters. That is the dissolved part. But the Na and the Cl now break apart from each other. So the NaCl is no longer a molecule of salt NaCl. It broke apart into its constituent ions. So when the atoms of the solute break apart into solution, forming an electrolyte, new word. Only electrolytes come from dissociation. And look what the next word is. Oh, electrolyte. So let's figure out what that means. But importantly, atoms breaking apart in the solution. Notice not molecules anymore. I get down to the atomic level when I dissociate. Electrolytes do just this. They light up as the light bulb. Part of your test for ionics and covalence was that light bulb test. So any solute that dissociates, allowing it to conduct electricity in solution. Definition of electrolytes. I do not believe it's the first time we've seen that word. Okay. Soluble. This is right off of one of the FETs that we ran. Able to be dissolved, forming a homogeneous solution. If it is soluble, it's able to be dissolved. Solubility, how much can I get to dissolve at that temperature? So slightly different play on the same word. Okay, both have to do with dissolving. It's just a different connotation of the word because the part of speech is different. So soluble versus solubility. Okay. Insoluble. Well, guess what? This means that it doesn't dissolve. So there you go. I see a precipitate forming. That yellow stuff is not dissolving, which is kind of cool. We'll do that in lab. Unable to be dissolved, forming a heterogeneous mixture, hence not a solution. Heterogeneous, two different things. Saturated. Here we go. So this is forming a saturated solution. You're stirring it up, and notice there's going to be some stuff left at the bottom that would not dissolve. That's what it's trying to show you. So let's get to this. Definition: a solution that has dissolved the maximum amount of solute at that given temperature. So I would make the analogy to a sponge that's holding as much water as it could. In this case, the liquid is holding as much of that powder as it can. It cannot. You put a little bit more in, and it just won't dissolve anymore. It's already done dissolved as much as it possibly can. Okay. Precipitate. Ooh, yuck. Here's one. This is a precipitate happening. It's two mixtures or two. It's a double replacement reaction going on, and it's forming that solid brown that's eventually going to form and fall. It's already formed, I'm sorry, but it's eventually going to fall out. You'll see it'll get heavy and it'll start to settle. So it's the insoluble product formed in a solution. Could be solid or just cloudy. Precipitate we've heard of before is like rain, and that's, I think, part of the reason why we use that is because when in the solution you see it happen, it literally is going to look, some of it like snowflakes, and just all settles, but it's solid stuff that is no longer soluble. And that's the end of video 3 when we do double replacement reactions and predict precipitates. And then we're going to do it in lab as the first lab, the precip lab. So we're going to get a firsthand experience on what a precipitate is and how it works. All right, supersaturated. So I have saturated and now I have supersaturated. This is a cool GIF of a solution that was supersaturated. At that temperature, it was technically holding more of that stuff than it was able to. And then you either tap it or add a seed crystal, and all the stuff that was in solution that shouldn't be there because it shouldn't be able to hold that much at that temperature drops out. And they're kind of fun, but man, making them is not easy, especially to get it back into a supersaturated form before the next class walks in. It's even harder. This is a solution that has dissolved more solute than it should be able to at that temperature. Okay. Supersaturated. It's holding more than it should be able to. Super is above. Concentration. Probably maybe the first time you've heard of concentration is the difference in concentration gradient that powers osmosis. So hopefully we can activate some prior knowledge. This is the amount of solute per solvent or solution. Amount of solute per solvent. So now it's part over whole. Here we go. And I can get into concentration and we can turn this right into molarity because if we put moles on top, we're ready to rock. Concentrated and dilute. You can see here we have more concentrated on my left side and more dilute on my right side. The relative comparison of solutions based on the amount of solute per solvent. That's key, because if there's almost no solvent, it's probably pretty concentrated. If that's all the same amount of solvent, then I can just compare the amount of solute, which is what we try to do. Okay, molarity is a specific form of concentration, moles over volume, which is liters in this case. So this is moles of solute per liters of solvent. Okay, it's right in the molarity calculation in table T. Under concentration, you'll also find parts per million. This is ppm, a measure of concentration for very dilute solutions, the mass of solute per mass of solution times 1,000, or times a million. This is used for stuff of very, very small quantities. Something that might infect the environment even in small amounts, like mercury. Okay, we can measure in parts per million because it's so small. Percent by mass or volume, very much the same as what you would expect to see. And I think percent by mass is on the reference table, but volume isn't, but it really is the same equation. Ratio of solute solvent based on mass or volume in terms of percent. So part over whole. Mass of the solute versus mass of the solution. Volume of the solute versus volume of the solution. Okay. Part over whole, percent. Boiling point elevation. So this is a kind of a picture of what's going on. And actually use something like this very much to explain what's going on. So this is just happens to be the piece that helps us. Freezing point depression is how we make ice cream. This is the effect solutes have on the physical parameters of the solvent. So it blocks them from coming into solid form and freezing, hence lowering the freezing point. It also blocks them from escaping and elevates their boiling point. So some things we can do to make water boil better in Denver, Colorado, where we learned the vapor pressure is, or the atmospheric pressure is lower. So in order to make it boil at a higher temperature, we add salt to the water, and all of a sudden it boils at a higher temperature, and I can cook my noodles better in Denver. And with that, we are done. All right, we got 2 out of the way. Happy trails.